Hello guys and welcome to another calculus video. In this video on the Advanced Integration Methods series, we are going to go over Feynman's trick or the Leibniz rule, whatever you want to call it. It's very popularly known as the favorite integration method of physicist Richard Feynman. So that's why it's often called Feynman's trick, and that's mostly what I'll be calling it. So let's go ahead and get right into it. So what's the purpose of using this method? Well, what this method does is it allows us to convert difficult integrals into simpler ones, then evaluate them and then transform them back into the original problem. And this integration method is applicable to a wide variety of different integrals, which means that it's very, very useful in the toolbox of anyone who wants to learn integration. It's instrumental in the creation of lots of generalized formulas, which I'll show you later, and it's super easy to learn and use as long as you learn it the right way. Also, it should be noted that Feynman's trick is more of a tool rather than an integration method, often in integration because you'll usually combine it with some other methods such as the Laplace transform, power series, or King's property. So let's go ahead and get started. So what exactly is Feynman's trick? Technically, it's called differentiation under the integral sign, but it's popularly known to be the favorite method of famous physicist Richard Feynman. So what it says is if we take the derivative with respect to t of the integral from a to b of some function of x and t dt, this is the same as integrating some function from a to b, and that function is the partial derivative with respect to t of f and x and t. Now, what exactly is a partial derivative? So go ahead and skip this section if you already know what a partial derivative is and how to take it, but essentially this symbol right here means the partial derivative with respect to t. Don't worry if you're not familiar with partial derivatives. The only thing you need to know how to do is to take the derivative with respect to t and treat x as a constant. And that's why we call it the partial derivative, because we have two different variables, x and t, but we're only taking the derivative with respect to t and we're treating x as a constant. Another way you can do this is you can differentiate using implicit differentiation and write dx, and whenever you see an x, just use dx dt, and then just set dx dt equal to 0. So here are some examples right here that I can go over. The partial derivative of sine of t squared x with respect to t is going to be x from the chain rule, because x is the coefficient of t squared, times 2t, again from the chain rule because that's the derivative of t squared, times cosine of t squared x. The partial derivative of tan inverse of tx is going to be x from the chain rule, and then on the bottom we have t squared x squared plus 1. And the partial derivative with respect to t of x to the t equals x to the t times natural log of x, because that's the natural log of the base. So here are a few quick practice problems for those of you not super familiar with this. Go ahead and try those if you like, or if not, you can go ahead and move on to the next section. Notice that I changed the variable names here. It's important to be able to take the partial derivative regardless of what the variable is. So just take the derivative with respect to the variable shown and treat every other variable as a constant. Alright, so hopefully you were able to do those. Now let's go ahead and get back to the definition of Feynman integration. So now hopefully this makes a little bit more sense. If we have some function that's defined by an integral, then when we differentiate that function, it's the same as taking... I'm sorry about this. I just realized right now. This dt should actually say dx right here. Let me go ahead and fix that. Yeah, so if we're integrating with respect to x and we take the derivative with respect to t, all we have to do is take the derivative of the inner function with respect to t and treat x as a constant. Okay, that's much better. So again, the partial derivative, or the derivative with respect to t of the integral from a to b of f of x and t dx is equal to the integral from a to b of the partial derivative with respect to the partial derivative of f of x and t dx. So this is a super general definition, and there's a more general definition of this that has more terms and stuff, but we're only going to really deal with this version since there's no other version of the formula that's all that useful for us. So how do we use this rule? So I'm going to go ahead and go over the steps to use Feynman integration. So let's say I'm trying to find this integral I, and this integral I is the integral from a to b of f of x dx. And f of x doesn't have an elementary antiderivative, so I have to instead use another method. So we're going to introduce a parameter, which is essentially just adding in this variable t. So I of t is going to be equal to the integral from a to b of f of x and t dx. Now I want f of x and alpha to equal the original f of x for some value of alpha. And what this means is if I plug in t equals alpha, then I of alpha is just going to be our original integral I. Also, I want I of beta, or the integral from a to b of f of x and beta, to be known for some value of beta. That way, you'll see why we need that later. So we're going to differentiate, so we're going to get I prime of t, and this is going to be the derivative with respect to t of this whole thing. So again, we bring the derivative inside, and so we're going to get the partial derivative of f of x and t on the inside. Then we're going to integrate this function with respect to x. So the idea is once we've taken the partial derivative with respect to t, this function f of x and t becomes much, much easier for us to actually integrate. And so this leads us to get some value of I prime of t that's completely in terms of t with no integral or anything. It's just some function of t. Then we're going to integrate I prime of t from beta to alpha, and this time we're integrating with respect to t since x is no longer there. And we're also going to do that with g of t. Now, hopefully g of t is a very simple function that we're able to integrate from beta to alpha just using normal integration. And then when we integrate I prime of t from alpha to beta, we're going to get I of alpha, which remember was our original integral I, minus I of beta. And we remember I of beta is a known value. So this means that I of alpha is equal to our original integral I is equal to I of beta plus the integral from beta to alpha of g of t dt. So essentially what we did was introduce a parameter, differentiate with respect to that parameter, then solve the original integral, then we integrate back the parameter so that we can get our original function. So it's a little bit complicated, but I'm going to show a few worked examples so that you guys can get the hang of the idea. So let's take a look at an example. This is sourced from the Cambridge integration bee from a couple years back. So our integral is the integral from 0 to pi of natural log 1 plus cosine x over 3. And instead, we're going to introduce a parameter here so that we have a function I of b, which is the integral from 0 to pi of natural log of 1 plus b cosine x over cosine x dx. Now, cosine x is just a constant, so we don't need to worry about that when differentiating with respect to b. But anyway, we differentiate, we get 1 over 1 plus b cosine x, and then we multiply by cosine x because of the chain rule. Of course, this is calculating I prime of b. So we get the integral from 0 to pi of 1 over 1 plus b cosine x. And then after using the Weierstrass substitution, this is easy to evaluate, so I'm not going to go ahead and go through all that, but you end up getting that I prime of b equals pi over square root 1 minus b squared. And so we can see that I of b is just going to be pi times sine inverse of b plus some constant c. Now, if we look at our original definition of I of b, we see that if we set b equal to 0, then we get natural log of 1, which is just 0. So our function is 0 over the entire domain of integration, which means that we know that I already have this down here. Yeah, natural log of 1. So that's just 0, which means that I of 0 is 0. And this allows us to solve for c, and we find that c equals 0, which means that I of 1/3 equals I is going to equal pi times sine inverse of 1/3 plus c. Why is there a plus c? There should not be a plus c here. It's just pi sine inverse of 1/3. I'm so sorry. You can also choose to integrate definitely, which means rather than calculate sine inverse, we calculate integral from 1/3 of 0 to 1/3. We find that I of 1/3 minus I of 0 is equal to pi sine inverse of 1/3, which is just this integral on the right here. And then we know that I of 0 is 0, which tells us that I equals I of 1/3 equals pi sine inverse of 1/3. So as you can see, we introduce the parameter, we differentiate with respect to the parameter, which gives us an easier integral to solve. Remember the Weierstrass substitution, that wasn't too difficult to do. Then we reintegrate with respect to that parameter and get our original function, and get the original integral function. So now that you know how to use this method, let's try some practice where I already tell you how to put the variable. or where to put the variable. So the hard part with Feynman integration is not really these steps of differentiating and then integrating, because that's all sort of just like brute math, just taking derivatives and doing elementary integrals. The hard part is figuring out where to put the variable. So for this first part, I've told you where to put the variable. So let me show you what I mean. And so, for example, for this first one, you're supposed to calculate this integral, and this is the integral function you're going to use. So all you have to do is differentiate with respect to b, solve the integral, then integrate with respect to b, and solve for the original integral over here. So that's not too difficult. Later on in the video, we'll get to trying to figure out how to actually come up with this parametrization right here. So go ahead and try all these practice problems. All right, I have some more problems down here. Oh, no, I guess I don't. It's just these 3 practice problems right here. All right, hopefully you were able to figure all of those out. So let's talk about how to choose a parametrization. So ultimately, knowing how to use Feynman's trick is easy to learn. The hard part is actually choosing the parametrization to make, as I said before. There are 3 important things you have to take into account. First of all, you have to know one value of I of b as a starting point. This can be for any value of b within the domain of I of b. And this can even be knowing the limit as b goes to infinity of I of b. It doesn't have to be an actual value of I of b. Even it can just be a limit. Typically, it's going to be I of 0, but that's not always the case. It really just depends on your function. Then after differentiating, the resulting integral has to be possible and hopefully easy to evaluate. So hopefully you're able to do it using just normal elementary techniques. You might have to use some more difficult methods, but the goal is to make it easier to solve. So if after you differentiate, you end up with an integral that's even more difficult to solve, then clearly the Feynman integration didn't work, and you need to place your parameters somewhere else. So this is super easy to check. Just differentiate and figure out if you can solve the new integral. And the third and hardest part about choosing a parametrization is once you've integrated with respect to x, you have to integrate I of b from your starting point to the value of b such that I of b equals I. What that means is the alpha in our first example right there. So when I say the value of b such that I of b equals I mean, for example, 1/3 in the problem we just solved, or alpha in the original example. So this is the hardest part to figure out because sometimes you may go through the whole problem just to figure out your parametrization failed. It's really hard to see when you place the parameter whether or not once you differentiate and then integrate, you're going to be able to integrate again. So this is really just trial and error. Obviously, you're going to get better at it the more you practice, and you're going to get a lot of intuition, but in general, this third step is where you're going to end up making the most mistakes, because those first 2 steps are really easy to check to make sure that they work, but this third step, I mean, it's really just going to be trial and error. So here's some common parameters or tricks to know to kind of get you started. So if you have some sort of integral that looks like f of p plus g of x over g of x, you want to try I of y equals integral from a to b of f of p plus y g of x over g of x. And the reason we want to do this is because once we differentiate with respect to y, because of the chain rule right here, this y times g of x, this g of x comes out, and so it cancels with the g of x on the bottom. So we just end up with f prime of p plus y g of x, which is really, really helpful. And this is a much easier to integral to solve as long as f prime is pretty simple than this one with g of x on the bottom, especially if g of x is something like sine of x or cosine of x. So that's a good trick to know. If you have x over f of x, this is actually a very similar situation. You can try, this looks a little bit silly, but I of y equals the integral from a to b of f inverse of y f of x. Now notice, if we set y equal to 1, then we just end up with our original integral because we have f inverse of f of x. And when we set y equal to 0, we just end up with f inverse of 0 over f of x. So those are two really, that y equals 0 is probably going to be your starting point, and y equals 1 is your sort of ending point, right? But once you differentiate, because we have this y times f of x, the f of x is going to come out because of the chain rule, and it's going to cancel with f of x on the bottom. So this doesn't look super simple, but trust me, in a lot of situations, well, not a lot, but there are quite a few situations where this will be a lot easier to evaluate than this right here. So that's the reasoning behind this. This one's a very similar one. If we have integral from a to b of natural log of p plus f of x, we can again put that y next to f of x, or we can put that y where the p is, so y plus f of x. And the reason for this is because once we differentiate, we'll often get an easier integral to solve right here because it doesn't have this natural log. I mean, if you think about it, if you're trying to integrate natural log of just natural log of x even, you have to use integration by parts. You can't use normal integration. So natural logs in general are nasty to deal with. On the other hand, reciprocals aren't all that hard to deal with. So that's the goal right there. And then another situation is if you have some power of x in the bottom, you can try I of y equals f of yx over x to the n, because when we differentiate, we get one of those x's coming out, and so the order on the bottom goes down 1. Something interesting is if you actually differentiate multiple times, if you differentiate n times, for example, you can completely get rid of that x to the n, which is sometimes very helpful. So let's look at, this is by far the most important pattern to know. If you have some f of alpha x minus f of beta x, where beta and alpha are constants, you can try, and all of this is over x times some other function g of x, you can try I of y equals f of yx minus f of beta x. And the reason for this is, you notice that if we set y equal to beta, we just end up with 0 on the top, and so that's a good starting point because we know that I of beta is going to be 0. And when we differentiate with respect to y, this f of beta x disappears because it's not related to y at all, and this x on the bottom also disappears because of the chain rule, and this is a lot easier to deal with than this nasty function right here. So this is incredibly important and common, and this is probably the most important pattern that you're going to see when you're solving these types of problems. It comes up a lot more than these other patterns that I've shown you, but in general, if you notice any of these patterns, try these parametrizations because they're sort of like a go-to and they work in a lot of different situations. So again, it won't always work, but it will often work out to your benefit. So to be honest, the best way to get better at recognize when and how to use Feynman's trick is through practice and trying lots of examples, which I have a lot of practice problems at the end of this video if you want to go ahead and try that. And the reason behind this is your brain will start to recognize patterns, for example, these patterns that I have up here, but also other patterns that maybe I didn't think of, or just in general with very specific functions and situations. So your brain will recognize these patterns in certain integrals. So in the meantime, when you're still trying to train your brain to do this, you want to try as many examples as you can, and you want to try placing the parameter everywhere. In all sorts of different places. You could try raising some function to the power of a parameter. You could try putting it next to x and then differentiating and getting that x out. You want to try everything. I mean, not necessarily everything, but you want to try as many different situations as you can because you never know which one is going to actually work. So let's talk about a little bit of a different situation. This is actually a different method than Feynman integration, but it still involves differentiating under the integral sign. So the best way I can sort of show this is through an example right here. So sometimes it's better to, rather than parametrizing our original integral, we can take an already known general integral formula and apply differentiation under the integral sign, often in multiple times. So what this looks like is if I wanted to solve the integral from 0 to 1 of x to the 5/6 natural log squared of x dx, this would be some really nasty integration by parts and annoying fractions to deal with. However, there's an easier way. We're going to use the integral formula, integral from 0 to 1 of x to the a equals 1 over a plus 1, equals 1 over a plus 1, which is super easy to prove for anyone. I mean, it's just power rule, right? Obviously, a has to be greater than -1, but that's not really of much importance in this situation. So what we're going to do here is, rather than setting this equal to I of a and then differentiating with respect to a and then integrating again, we're just going to take this original formula and we're going to differentiate with respect to a. So what happens is when we differentiate with respect to a, this x to the a becomes x to the a times ln x, and then this just becomes -1 over a plus 1 squared. And guess what? We can just go ahead and do this again, because this didn't really change the inside function that much. It just multiplied by ln x. So if we differentiate again, we multiply by ln x a second time. And now we have x to the a ln squared of x dx integrated from 0 to 1 equals 2 over a plus 1 cubed. Then we just set a equal to 5/6, and we get our answer pretty easily. Just doing some basic maths, we get the integral from 0 to 1 of x to the 5/6 times ln squared of x is 432 over 1,331. So this is typically used in tandem with two interesting situations here. If we take the partial derivative with respect to y of some function raised to the y power, then we get that function raised to the y power times the natural log of the function, because the function was the base. And that's what we just used up here. So this is really, really common to see. So if you see in some integral some natural log of some other function, you want to think, well, what if instead of natural log, I had that function raised to a power? Would that integral be easier to solve? And if it is, then you can go ahead and solve the integral with the function raised to a power, and then take the partial derivative with respect to that power. Does that make any sense? I'll show you some more examples in a moment. And another situation that this is commonly used with is if we have 1 over a plus y f of x, when we differentiate with respect to y, because we have this reciprocal here, we get negative f of x over a plus y f of x squared. And notice that this 1 over, this is just a reciprocal, right? This is all raised to the negative 1 power, but with a simple differentiation, we got it raised to the negative 2 power, which is very, very, very helpful in many situations, because obviously it's going to be harder to deal with some function squared on the bottom than just some function on the bottom. So that's something to keep in mind as well. I have an example. I have some useful formulas to work off of here. So these three formulas right here, really often you're going to be using these in the same way that I just showed. So for example, integral from 0 to infinity of x to the k over x to the n plus 1 dx equals pi over n cosecant of k plus 1 over n times pi. And so the way you might use this formula is if you take the partial derivative with respect to k on both sides, you're going to be able to calculate it pretty easily on the right side, and on the left side, you'll get x to the k ln x, right? Which now allows us to calculate a lot of different integrals that we hadn't seen before. Another example here is two different representations of the beta function, one of them with power functions, which is very similar to this integral up here, and the other one with trigonometric functions. Also, if you want to watch my video on Ramanujan's master theorem, you can go ahead and do that, and that will explain this odd-looking formula right here. But essentially, this formula will come up pretty often because if we take the partial derivative with respect to s on both sides, or actually just the derivative with respect to s, then we get x to the s minus 1 times natural log of x times f of x, which can be really useful for introducing that natural log in situations where it does not seem very favorable. So let's go ahead and look at an example. If I wanted to calculate the integral from 0 to pi over 2 of natural log of cosine of x, I could take a look at I of alpha, where I of alpha equals the integral from 0 to pi over 2 sine of 2 times 1 half minus 1, which is just 0 of x, and this just means sine of x raised to the 0 power, or 1, times cosine to the 2 alpha minus 1 dx. And essentially what this is it's just the integral from 0 to pi over 2 of cosine 2 alpha minus 1 of x, but I'm just putting it in a form where I can easily see that my beta function variable right here is going to be 1/2. So we have gamma of 1/2 and gamma alpha plus 1/2. Then I differentiate with respect on both sides with respect to alpha, and I get 2 times the integral from 0 to pi over 2 cosine to the 2 alpha minus 1 of x times natural log of cosine of x dx. And this is just some nasty gamma and digamma functions on the right side, but all I'm going to do now is plug in alpha equals 1/2. So I plug in alpha equals 1/2, and I get that I prime of 1/2, which is equal to 2i, since if you plug in 1/2 right here, you get cosine to the 0x times natural log of x, and that's times natural log of cosine of x, which is just natural log of cosine of x, which is our original integral. So we have 2i equals 1/2 square root pi, and then some nasty stuff with the gamma and digamma functions. And anyway, once you simplify everything, you find that 2i equals negative pi ln 2, which means that our integral I is negative pi over 2 ln 2. And again, there are definitely better ways to do this, but notice that we just had 3 or 4 lines of work right here because we recognize that this is a representation of this beta function formula right here. So that's going to be really helpful. If you ever see integral from 0 to pi over 2, powers of sine, powers of cosine, and natural log sine, natural log cosine, think partial derivative with respect to alpha and beta in this formula right here. All right, let's go ahead and move on to the next topic. Repeated differentiation under the integral sign. So rarely it may be helpful to take the derivative of the integral function multiple times and then solve the resulting differential equation. This typically occurs with trigonometric functions in the integrand. So the examples that we just did are examples of taking the derivative multiple times, but sometimes you'll take the derivative multiple times and then have to integrate that function back. So I'm going to go ahead and try this example right here. I really suggest you guys try this example before I go ahead and show the solution, but if you don't feel up to it, then I will show you the solution right now. So go ahead and give it a shot. All right, hopefully you will be able to figure it out, but I'm going to go ahead and show the solution right here. So we have I of a equals integral from 0 to infinity of sine cubed of ax over x cubed dx. We differentiate with respect to a, and we get 3 sine squared of ax cosine of ax over x squared. Notice that the power of x in the bottom decreased because we had that chain rule x coming out. So in order to keep getting rid of the x's in the bottom, we can keep differentiating with respect to a, I mean. So the first thing I did was I sort of reorganized these terms a little bit, and then I used the sine product to sum formula. So we now have cosine ax minus cosine 3ax over x squared. Differentiate again with respect to x, and I get I double prime of a, the second derivative of I with respect to a, is 3/4 times the integral from 0 to infinity of 3 sine of 3ax minus sine of ax all over x dx. And now I just plug in the formula that was given right here. A is greater than 0. We're only talking about a is greater than 0 for this as well. So when we go ahead and plug that in, we're going to get that I double prime of a equals 3 pi over 4, which means that I prime of a, just integrating both sides, is going to be 3 pi over 4 times a plus c1. But notice that I prime of 0 equals 0, which means that c1 also equals 0. And then I of a, after integrating again, is 3 pi over 8 times a squared plus c2. And again, I of 0 is 0, so c2 is also 0, which means that I of 1 equals I equals 3 pi over 8. So I think that's a pretty interesting problem, and that was pretty straightforward since all we had to do was repeatedly integrate the second derivative of I of a. But in some situations, you may have to find that, for example, the second derivative of I of a equals some constant times our original I of a, which means you'll have to solve a little bit of a different sort of differential equation. But overall, I think the differential equations are not the hard part. The hard part is definitely choosing that parameter. So one thing to note is that Feynman's technique is best used alongside other methods. It's not very often that you're only going to use Feynman's method, and you're not going to use any other method. So it's really important to learn how to use it well, because when you're focusing, you want to be able to focus on the more difficult methods, like applying power series or using the Laplace transform, or even doing contour integration, or something like Ramanujan's master theorem. So you definitely want to be able to use Feynman's trick well and easily and have it really locked in, because you won't get caught up trying to do the Feynman integration. It'll flow really naturally, and you can focus on the more difficult method. So for this purpose, I provided as many practice problems as I can find, and I absolutely implore, I'm saying this is super, super important. If you want to use this method for integration, please try to solve as many as you can, because trust me, it will be helpful if you plan to use this method for integration. Sorry about all the typos in this. I found these problems from YouTube videos and comments, integration bees, and online resources. So some of them were just from Google search or from Math Stack Exchange. But please, please, please give these problems a shot. Contact me in the Discord if you need any help trying to figure them out. I'm always happy to help. And yeah, so let's go ahead and look at all these practice problems. Make sure to remember those patterns that I talked about earlier. Notice that the stars represent not exceptionally, but extra hard problems. So here are our first 6 practice problems. Alright, hopefully you were able to figure those out. Here's another set of practice problems, the next 6. Yeah, so for these problems, for this number 11, you're going to use the fact that sine x over x integrated from 0 to infinity is pi over 2, which you could have proven in the last problem. Alright, let's go ahead and look at, I believe this is the last set of practice problems. No, it's not. Here's another set of practice problems right here. Lots of stars here. These mean harder problems. And our last 2 practice problems are down here. So hopefully you were able to figure out most or all of those practice problems. Again, please go ahead and join the Discord and ask me for help if you want any help trying to figure out these problems, because doing examples and figuring out solutions to different problems is really the only way that you can improve with Feynman integration, because it's just something that's so intuitive once you've learned it. Obviously I can give you tips and patterns to look for, but overall, it comes down to how comfortable you are with Feynman integration in general, right? If you're more comfortable with it, you're going to be better at it. So do as many examples as you can and keep practicing and looking for harder problems, and you're going to be set. Yeah. So if you want to learn more about integration, you can check out my previous videos on contour integration. I have a 4-part series that goes very, very in-depth with that. Or you can stick around for future videos where I'm going to be going over King's property and the Laplace transform, and hopefully some other methods after that. But overall, thank you for watching. I really, really hoped you learned something. And again, I'm always available to ask any questions. So yeah, I hope you guys enjoyed the video. I hope you learned something, and I'll see you next time.